Welcome everybody to Algebra 2, Section 2.1. Here we're going to be doing one-step equations. So suppose my Algebra 1 class has 25 students and my Algebra 2 class has 25 students, so the same number in each. If each class adds 2 new students, the number of students in my classes would still be equal. So let me show that here. Okay, so we have 25 in Algebra 1 and 25 in Algebra 2. And in each class, we take that 25 and add 2 more students. We end with the resulting 27 students. So it stays the same. And this example illustrates the addition property of equality. And the addition property of equality, as defined below, states if an equation is true, such as 25 equals 25, that's true, and the same numbers added to each side, or up above we had 2 and 2, then the resulting equation is true, such as 27 equals 27. So if it starts true, we add the same thing to both sides, it's still true. So for any numbers a, b, and c, if a equals b, then a plus c would be the same thing as b plus c. So a numerical example would be like if you had 5 equals 5, and we took each 5 and added 1 to it, we'd end up getting 6 equals 6, and it's still true. Now, equivalent equations, more vocab here, equivalent equations have the same solution. And to solve an equation means to find all values of the variable that make the equation a true statement. We do this by isolating the variable, and isolating just means getting it on one side by itself with a coefficient of 1. One side of the equal sign of a coefficient of 1. I'm going to talk a lot about sides here, and sides always refer to sides of the equal sign, either the left of the equal sign or right of the equal sign. So here we have these three equations here. So in number 1 here, solving the equation, we're supposed to check our solution. R minus 8 equals 32. So R is right here. Our ending goal is to get R equals some number. That's our goal in all of this. And so in order to achieve that goal, we need to get R to be the only thing on that side of the equal sign. And so we need to get rid of this subtracting of 8. So we ask ourselves, well, what's the opposite of subtraction? Well, the opposite of subtraction is addition. And more specifically, the opposite of subtracting 8 is adding 8. And if we do negative 8 plus 8, we end up getting R plus 0, which is just R. Which, once again, our goal is to get R equals some number, so we're very close to getting just that now. Now, like we set up above, though, we said that if we add something to one side of the equal sign, that we also need to add it to the other side in order for it to stay true. So if this is a true statement up above, we have to add the same thing to both sides of the equal sign for it to remain true. Just like my Algebra 1 class and my Algebra 2 class, if I add 2 students to one class but not the other, they don't remain at an equal number. I have to add them to both classes. So here now on the right side, I get 32 plus 8, and that would be 40. And so now I have R equals 40, and that's my answer in the format R equals a number. Now we can plug this in to check our work, and I don't require this, but it's something that you can do every time. And how we check our solution is we replace R with 40 in our original equation, since 40 equals R. Similar to when we simplified expressions where we had to plug in numbers for variables last unit. So if I were to do 40 minus 8 and say, does this equal 32? I like to put a question mark above it because I'm asking the question, does that equal? And 40 minus 8 is in fact 32, and 32 equals 32. So I put a little check there saying, yep, it worked out just fine. I checked it and it's good. And once again, checking your solution is something you always can do, but it's not something I necessarily require to be done. On number 2 here, 8 minus 12 equals negative 27. So if I add 12 to both sides, I will undo the subtraction of subtraction of 12. And so negative 12 or minus 12, remember negative and minusing a number are really the same thing, give us 0, and we get h plus 0, which I can just call h, equals, if I add 12 to one side, as I mentioned above, I have to add it to the other in order to keep it true. And negative 27 plus 12 is negative 15. opposite sign subtract, and you keep the sign of the bigger number. And that's our answer. H is negative 15. And if you were to plug that back in, you would end up getting negative 15 and negative 12, or negative 15 minus 12, which is, in fact, negative 27. On number 3, we have 5 equals x minus 10. So x is being subtracted by 10. We undo the subtraction of 10 by adding 10. Remember, our goal is to undo things around the variable to try and get the variable by itself. And negative 10 or minus 10 plus 10 is plus 0, and we don't need to write that down. And if we add 10 to the other side, we get 15 equals x. And 15 minus 10 is, in fact, 5 if you were to plug it back in. Now, when isolating the variable, getting it by itself, it doesn't matter if the variable is on the left side of the equal sign or the right side. For example, see this number 3 above. We had x on the right side, and we still regarded that as true. So you could just as easily flip it around if you prefer. If you're like, I'd much rather have my variable on the left just to stay consistent because that makes more sense to you, feel free to do just that. Next up, we're going to solve using subtraction. So very similar to the addition property of equality, the subtraction property of equality can also be used to solve equations. So the definition here, if an equation is true and the same number is subtracted from each side, the resulting equation is true. So quite literally, the only change between this definition and our addition property of equality definition is it says subtracted instead of added. So for any numbers a, b, and c, if a equals b, and if we take a minus c and b minus c, they will equal each other as long as we subtract the same number from both sides. So it's not like one's c and one's d. So an example here, if I were to pick the number 4 and I say 4 equals 4, and now I subtract each side by 2, I get 2 equals 2. So it started as a true statement. We subtracted the same thing from both sides of the equal sign, and it remained a true statement at the end. So on number 1 here, as we solve the equation and then check the solution, once again, checking is optional. I'll show it on the first example, is once again, our goal is to get k to equal some number. K is not currently by itself, it's being added by 63. So we have to undo the addition of 63 in order to get k by itself. And the opposite of addition of 63 is subtracting 63. And 63 minus itself is 0. And we get k equals, or k plus 0 equals, and I don't need to write the plus 0. But as we saw up above, I have to subtract 63 on both sides in order for it to remain true. Up here, if I had only subtracted it on one side and not on the other, we'd have gotten 2 equals 4, which isn't a true statement. For it to remain true, we had to subtract it from both sides of the equal sign. So I subtract the other side by 63, once on each side of the equal sign, and we end up getting 92 minus 63 to be 29 as our answer. And some of us might benefit from drawing a line through our equal sign. That way we can visibly see a left side and a right side. That's something that can help some of us. And so that might be a visual tool that you use to help you out. Now I did mention that we could plug this back in. So we do 29 instead of k, because they equal each other, it's the same thing, plus 63 equals 92. Once again, I'm going to put that question mark above because I'm asking, does it equal? And so I plug this in here, and I end up getting 92 equals 92. And yep, I checked it out and it worked. So on number 2 here, 7 equals 42 plus t. So 42 is adding with t, and so to get rid of a positive 42, we subtract 42. And the 42 minus itself is 0. So I could either put 0 plus t, or I can just put t. Notice I am putting a tail on my t there to differentiate it from a plus sign. But if I subtract 42 from one side, I have to subtract it from the other, and I get negative 35 equals my variable t. On example 3 here, 21 plus q equals negative 18. As I mentioned before, some of us might benefit from drawing a line through here. I'll show that here on this problem, so we can visibly see the left side of the equal sign and the right side of the equal sign. So I need to undo the addition of 21, and that way I just have q on this side of the equal sign. And in order to do that, here I'll subtract 21, and we get 0. So we get 0 plus q, or just q. But if I subtract 21 from one side of the equal sign, I have to subtract it from the other, and I get negative 39. And that is my answer. I have q equals to a number. Some additional examples that involve fractions or decimals. How fun. Here on number 1, y plus 4/5 equals 2/3. And this is an awkward non-gap there, but that is separate. That this is the equation here. Now y is being added by 4/5. So to undo that addition, we would subtract 4/5. However, I wouldn't write this down yet, is if we subtract 4/5 by 4/5, it does give us 0, and we do just get y on that side, but we can't do 2/3 minus 4/5 quite yet. So you can either do it inside the problem, or we can get common denominators outside the problem. So whether you want to do that here and just slash it out like I did, and feel free to go ahead and write this down now if you are wanting to do that, and do it off the side. Otherwise, you can do it inside the problem by trying to get common denominators here as well, and maybe just waiting to write it and knowing, hey, I'm going to have the common denominators in this part of the problem. But let's say I do it off to the side here, and I do 2/3 minus 4/5, and I need the bottom to be the same, so I need to think what number can 3 and 5 multiply up to, and that number is 15. So I multiply this equation, or this fraction, by 3/3, and this equation, or fraction, by 5/5. I get 10/15 minus 12/15. Now I subtract the numerators, and I get y equals -2 over, keep the denominator the same, 15, and that does not reduce. Number 2 here, 1 equals x plus 0.356. So x is being added by 0.356. We have to subtract that exact same number to undo it. But if I subtract it from one side, I have to subtract it from the other to keep it equal. And I'm definitely going to do my work off to the side here. 1 minus 0.356. When we add and subtract, it's very important we keep our decimal lined up. So 1 secretly has a decimal behind it with a bunch of zeros after that. And we could continue writing zeros, but we don't need to because I just wrote more zeros to match the decimals in the other number. Now as we go to subtract here, we go from right to left for when we have our vertical subtraction like this, or vertical addition. 0 minus 6. Well, we can't do that, so we have to borrow. But we can't borrow from this one, so we have to borrow from this one. And we can't borrow from there, so we have to borrow all the way from the 1. So the 1 becomes a 0, so that way the next number can become a 10. But the 10 becomes a 9, so that way the next one becomes a 10. But this 10 becomes a 9 again, so that way the last one can become a 10. And now we can actually subtract. 10 minus 6 is 4, 9 minus 5 is 4, 9 minus 3 is 6, drop the decimal, and 0 minus 0 is 0. So we end up getting x to equal 0.644. And whether you include that the 0 before the decimal or not is completely up to you. You could just call this 0.644 or 0.644. I do not care either way. Number 3 here, a plus 1 equals 2/7. So a is being added by 1. To undo that, I will subtract by 1. However, I can't just subtract 2/7 and 1 in order to get a by itself. I have to actually do that off to the side. So if I do 2/7 minus 1, which was secretly over 1, I need common denominators again. My common denominator will be 7. This one's already there. The other one is not. So I multiply by 7 on the top and bottom, and I get 2/7 minus 7/7. Now, if I actually do the math here, I have to subtract the numerators, 2 minus 7 to get -5, keep the denominator the same, and -5/7 does not reduce. And whether you put the negative on the top of the fraction, or in the middle of the fraction, or on the bottom of the fraction, it doesn't matter. Regardless, the fraction is negative. Practicing writing this an equation from a sentence. Write an equation for the problem, then solve it. So 14 more than a number is equal to 27. Find the number. So let's go piece by piece, just like we did in section 1.4 when we did this. 14 more than a number. So 14 more than plus a number, your variable, I'll call it x, is equals 27. So I'll write 27, and boom, I have my equation, just taking it piece by piece from left to right. Now I have to get x by itself now to find the number to solve the equation, and it's being added by 14. So I undo that by subtracting by 14, and 14 minus 14 is 0, and I get x. I subtract it from the other side to keep things equal, and I get 13, and so the number must be 13. That 14 more than 13 is equal to 27. On number 5 here, we're talking about the Washington Monument in Washington, D.C. It is built in 2 phases. During the first phase, the monument was built to a height of 152 feet. During the second phase, additional construction resulted in the monument's final height of 555 feet. That's a lot of feet. Must be stinky. How much of the monument was added during the second construction phase? Write an equation to solve the problem. So word problems can be very daunting for a lot of us, or very intimidating. And something that can really help with it is to highlight or circle or underline key information. So I'd encourage you to pause the video now and pick out information that you believe to be key or important to us solving this problem. And then play the video when you think you have it all and see what I highlight compared to you. So we don't really need to know that it's the Washington Monument, so I'm going to leave that unhighlighted. We don't need to know where it's at either. But we do need to note that it was built in 2 phases. And we need to note that the first phase, the monument was built to a height of 152 feet. And that during the second phase, we had additional construction. Additional is a math word, definitely want that there. Resulted, that's also a big word in math, in the monument's final height of 555 feet. And then here we want to know this. How much of the monument was added during the second construction phase? And then we're supposed to write an equation to solve. So I ended up highlighting here a good amount of stuff in this problem here. And if you highlighted maybe in this entire sentence, like the monument was built, use the right tool, the monument was built, that's perfectly fine as well. Or like you highlighted of the monument, that's okay too. I just like leaving those parts out because it makes it so I have a little bit less highlighted, and it makes the parts that are highlighted stick out a little bit more now. Now, a next good step is to define your variable. We've had variables on every problem we've done so far today, and we'll have a variable here as well. I'm going to go ahead and call my variable x. You can call it whatever you want. You have to figure out what is it representing. Well, remember that we've been solving for the variable. That's what we've been finding. So our variable is whatever we're supposed to find. And so what we're supposed to find is how much it was added during the second construction phase. So that's the question we're asked. How much was added during the second construction phase? So I'm going to say x is the amount added during the second phase. It's the amount during the second phase. And if you just wanted to put second phase, that's fine as well. Now we need to try and figure out an equation. So during the first phase, the monument was built to a height of 152 feet. So I'm just going to write that number down, 152. Then we know during the second phase we had additional construction, so I'm going to put in a plus sign because it says additional. And then it was additional construction from the second phase. So I'm going to call that x, like we mentioned earlier, because that's the amount of the second phase. So the amount from the first phase, 152, plus the amount from the second phase, x, results in the final height. So resulted and final both tell us, either one individually, tells us that we have an equal sign here. It totals a certain number, and it totals 555 feet. So if we take the amount during the first phase, add it to the amount of the second phase, we get the total amount of the monument. Now that we have this equation, we can go ahead and solve. X is being added by 152, so we subtract by 152. And 152 minus itself is 0, and we get x plus 0, which is just x. I have to subtract 152 from the other side of the equal sign as well, which results in 5 minus 2 from right to left being 3, 5 minus 5 is 0, and 5 minus 1 is 4, so we get 403. However, I am going to be a stickler that you have labels on word problems, so this isn't just 403, it's not 403 ostriches, it's not 403 candy bars, it's 403 feet. Moving on here to the next page, we're going to talk about solving problems by multiplication, solving these equations by multiplication. I started to say addition, but we've already done that. So if an equation is true, the multiplication property of quality, if an equation is true and each side is multiplied by the same number, the resulting equation is true. Very similar to our properties of the properties of quality for addition and subtraction, except for now we're saying multiplied. So for any numbers a, b, and c, if a equals b, then a times b, a times c is equal to b times c. You can multiply each side by the same number, and it'll still be true, if it started true. So a numerical example could be 2 equals 2. It's true, and if I were to multiply each side by 3, it would result in a still true equation, 6 equals 6. So it starts true, we multiply the same thing to each side, it finishes true. Let's use this to solve here. So on number 1, s divided by 12 equals 3. So once again, we're wanting to get s by itself to be the only thing on that side of the equal sign. And so to undo the division of 12, we have to think, what's the opposite of division? Well, the opposite of division is multiplication. So I'm going to multiply by whatever we're dividing by, 12. Now, some of us might really benefit from thinking of this as multiplying by 12 over 1, because now we have a fraction times another fraction, and we can cross-reduce. Some of us may notice that without putting it over 1, but some of us may only notice that when we put it over 1, so that might be helpful for a lot of us. Now, diagonally, we can cross-reduce 12 and 12. 12 goes into 12 once, and 12 goes into 12 once, meaning we're left with 1 times s, which is s, over 1, and s divided by 1 is just s. So we're left with s on that side, which is exactly what we wanted. However, if we multiply one side by 12, we just talked about above, that we have to multiply the other side by the same number for it to remain true. So 3 times 12 is 36, and s would equal 36. Once again, we can check our work. And to check your work, you plug that answer back in for the variable, and we take 36 divided by 12, and we say, does this equal 3? And the answer is that, yes, 36 divided by 12 is in fact 3. It checks out. Number 2, 1.8 equals 1.8 equals w over 2. So w is being divided by 2. To undo that, we do multiplication of 2, or 2 over 1, and those 2's reduce. They should always reduce at this step if you're doing it correctly, by the way, and we're left with w. We multiply the other one by 2, and 2 times 1.8. Some of us might benefit from just covering up the decimal for a second and saying 2 times 18 is 36. And then we just have to say, oh, one number was behind the decimal, one number is behind the decimal. Other of us might benefit from doing this off to the side, where we do 1.8 times 2. We do not need everything to be lined up by the where the decimal is when we multiply vertically like this. And we do 2 times 8 is 16, so I drop the 6, carry the 1. 2 times 1 is 2, add the 1 up here to get 3. And I say a total between these numbers of one number was behind the decimal, so we have a total of one number behind the decimal at the end. And regardless of how I go about it, I get 3.6 equals w. Number 3, n is being divided by 3 currently. So ignoring the fact that this side's a fraction, we're just going to focus in and saying, hey, what's happening to the variable? How do I undo it? Those are my two primary questions when I solve equations. What's happening to the variable? How do I undo it? So the variable is being divided by 3. How do I undo that? I multiply by 3, or 3 over 1, and those 3's reduce, and I get n. Now on the other side of the equal sign, if I multiplied one side by 3, I have to multiply the other side by 3, or 3 over 1. I'm going to pick 3 over 1 here because there's another fraction here in this case. And now as I multiply these, I look to cross-reduce diagonally, and 3 and 5 don't reduce because the only number that divides into both is 1. So I multiply straight across, and on the top I get 6, on the bottom I get 5, and I get 6 over 5, or 1 1/5, or 1.2. And it was a negative times a positive, which results in a negative. And I could put that negative out in front like it started, I could put it on the top, or I could put it on the bottom, and it truly does not matter. I'll put it out in front since that's how it started. Once again, it does not matter where we put it. Let's go on to... I'm actually going to skip this section for a moment, but I'm going to come back to it, okay? So let's just put a pin in that and these for a moment. It's more of the same, and I'm going to come back to those after we do the division. So division property of equality. There's actually a little bit different wording here on this one compared to the previous three. So if an equation is true and each side is divided by the same non-zero number, the resulting equation is true. So the highlighted things are what changed. So we're saying divided instead of multiplied, added, subtracted. We're clarifying it can't be 0. And that's because we can't divide any number by 0 because it breaks math. It's what we call undefined, or UND for short. Undefined or UND for short. Because you can't take things and split them into 0 groups. Even if you were to have not split anything up at all, it still is in one group, the group it's originally in, or they're all intact. So that's why it clarifies non-zero number, because we can't divide by 0. So for any numbers a, b, and c, if a equals b, then a over c equals b over c, provided that c is not 0, because once again, we can't divide by 0. So if I were to start with a true equation, 8 equals 8, and we were to take 8 and divide by 2 on each side, we end up with the resulting equation, 4 equals 4, which is true. So as long as it starts true, we divide the same thing on both sides, or by the same thing on both sides, we get a true equation to end. So let's work on solving these. So on number 1, 11w equals 143. So once again, focusing on what's happening to the variable, and then how do we undo it. So our variable is being multiplied by 11. The opposite of multiplication is division. So we'll divide by 11. And 11 divided by itself is 1. And you get 1w, or just w. But like we mentioned up above, we have to divide both sides if we divide one side. And so we divide both sides by 11. And 143 divided by 11, we could do that off to the side, for example. 11 doesn't go into 1, but it does go into 14 one time. And we multiply 11 times 1 and get 11. Subtract these two and get 3. Drop down that 3, and now we have 33. And 11 goes into 33 exactly 3 times to get 33, and we get a remainder of 0. So we get w equals 13 as our answer. And once again, we could go ahead and check our work if we would like. We would have 11 times 13 and say, does that equal, I asked the question here, 143. And sure enough, 11 times 13 is 143, and so it does in fact check out, just like an employee at a retail store would. It checks out. Number 2, negative 8x equals 96. So negative 8 is multiplying with x. To undo that multiplication of negative 8, I will divide by negative 8. And if I do it to one side, I must do it to the other. On the left side, negative 8 divided by negative 8 is positive 1, because the negative divided by negative is a positive. That's why it's important we divide by the negative as well, not just the positive, because we don't want it to be negative x equals a number. We want it to be x equals a number. On the right-hand side, a positive divided by a negative is the negative, when there's one of each sign. For multiplication division, it's a negative. And 96 divided by 8 is 12. Number 3 here, negative 0.42 equals negative 3s. So s is being multiplied by negative 3, so to undo that we divide by negative 3. And if we do it to one side, we have to do it to the other side to keep it remaining accurate and true. So on the right side, negative 3 divided by negative 3 is positive 1, and I get positive 1s, or s. On the left side, I know a negative divided by a negative will be a positive, but it might be hard for us to do 0.42 divided by 3. So I'm going to make this in here, 0.42 divided by 3. I'm going to bring up my decimal in the exact same spot it's in, and I say 3 goes into 4 one time, and we get 3, we subtract and get 1, bring down the 2, and we get 3 goes into 12 4 times exactly, and we get 0.14. So s is equal to 0.14, or just 0.14, the 0 being optional. Now, you also might be able to cover up the decimal for a second and say 42 divided by 3 is 14, and then put the decimal back with 2 numbers behind it like it was before. That might be a little bit of a mental math trick that you can use. So here, write an equation for the problem below, then solve the equation. Negative 14 times a number equals 224. So negative 14 times a number, so negative 14x for example, equals 224. That would be our equation. And now we solve it by dividing by -14. A positive divided by a negative on the right side gives us a negative, and 224 divided by 14 is 16. Now, let me go back and cover, before I get to these one-step equations at the bottom here to end our notes, let me go back to cover the fractions. Now, I'm going to get this in a moment. Before I do, let's explore number 5. We have 2/3 x equals 10. 2/3 x equals 10. So 2/3 is multiplying with x. And we just learned that typically if something's multiplying with it, we want to undo that by dividing, because that's how we undo multiplication. And so I would not write this down yet, but if I were to divide by 2/3, we say that anything divided by itself is 1, as long as it's not 0, and we get x. But when we do this other side, we don't really know how to handle this stacked fraction where we have 10 divided by a fraction. And so we have to remember, going back to our earlier math days, that we learned that dividing by a fraction is the exact same thing as multiplying by what we call the reciprocal. And the reciprocal just means the flipped version. And so maybe that's something you write right below that the reciprocal is that it means the flipped version. So if we multiply by the reciprocal of 2/3, that'd be 3/2. And let's look at what happens on the left side here. These 3's can cross-reduce to both become 1, and the 2's can cross-reduce diagonally to both become 1. And so you're left with 1 times 1, which is 1, 1 times 1, which is 1, and we have this x still, and 1/1 is just 1, which we don't have to write before x. We can just write x. On the right-hand side, if we multiply the left by 3/2, we have to multiply the right by 3/2, the reciprocal of the fraction multiplying with the variable. If I put this 10/1, I can cross-reduce the 5 or the 10 and the 2, and the 10 becomes 5, and the 2 becomes 1, because 2 goes into 10 5 times, and 2 goes into 2 once. So now if I multiply straight across, I get 5 times 3, which is 15. So multiplying by the reciprocal achieves the same result as as dividing by a fraction. To showcase that as well, if I were to take 4 and I divide by 2, I get 2. If I were to take 4 and divide by 1/2, multiply by the reciprocal of 2, the reciprocal of 2 is secretly 1/2, we also end up getting 2. And I could showcase that over here by saying 4/1 times 1/2. We can cross-reduce 4 and 2 to become 2 and 1, and we get, just as I mentioned, 2/1 or 2. So whether we divided by 2 or multiplied by its reciprocal, we got the same result. So dividing by a number or multiplying by its reciprocal are the same thing. So with that being said, let's practice number 6. We have 4/9 times w equals -8, and while we love to divide to undo a fraction or to undo multiplication, it's a fraction here, and so we multiply by the reciprocal instead, as my iPad glitches out on me. The reciprocal of 4/9 is 9/4, with the 9's reducing, the 4's reducing, and us getting w. Once again, that'll happen every single time on these. The side with the variable will reduce to 1 times whatever the variable is. Multiply the other side by 9/4, and putting the -8/1. -8 and 4 reduce to become -2 and 1 when you reduce by 4, and we end up getting, as we multiply straight across, -18/1, which is -18. Number 7 here, -6/5k equals 12. So we'd love to divide to undo this, but that creates a stacked fraction, or as I like to call it, a double-decker fraction. So instead, I'm going to go ahead and multiply by the reciprocal, -5/6, taking important note to keep the same sign, because a negative times a negative results in a positive. That way, when the 5's and 6's reduce, we're left with positive k. If we multiply one side by -5/6, we have to do the other. Once again, the negative really could go anywhere on this fraction. Putting 12/1, we can more easily cross-reduce, with 12 and 6 reducing by 6 to becoming 2 and 1. And multiplying straight across, 2 times -5 is -10/1, or just -10. Number 8 here, we have -1/2m equals -9. So we're going to multiply by the reciprocal here, and you get -2 or -2/1 if you prefer. Those -2's reduce, and the negative times the negative is a positive, and we get m. Multiply the other side by -2 or -2/1 if you wanted, and we get nothing reducing, but negative times the negative is a positive, and 9 times 2 is 18. Some additional examples that may or may not work out as nicely. On number 1, once again, we have a fraction multiplying with a variable. We'd love to divide to undo that, but with fractions that gets messy, so we multiply by the reciprocal, in this case 5/3, with 5's reducing, 3's reducing, and just being left with 1k or k. On the other side, multiply by 5/3 and put that 6/1 to help us visually see what's going on. And 6 and 3 reduced by 3 to become 2 and 1. Multiply straight across, and 2 times 5 is 10. Over 1 on the bottom, we can just put 10. On number 2, -1/4 equals 2/3 times b. Now I'm going to do something wrong here on purpose, and I hope you can catch it. So I see a fraction here, so we're going to multiply by the reciprocal. Did anybody catch what I did wrong there? Well, here is the fraction multiplying with the variable, and that's what we're supposed to be using the reciprocal of. So I don't care what's on the other side of the equal sign when I'm planning to do this. I'm saying there's a fraction with the variable. That's what I care about. If I crossed everything else out and just focused solely on the side of the variable, we can see, oh, we'd multiply by 3/2 in order to get b by itself when we reduce the 3's and the 2's. And now, because the other side's a variable, when we multiply, we'll have a variable times a variable and not have to put anything over 1. Diagonally, 3 and 4 don't reduce, and 2 and 1 don't reduce. So we just multiply straight across and get 3 on top, 8 on the bottom, and a positive times a negative is a negative. Once again, whether the negative's out in front of the fraction, on the top of the fraction, or the bottom of the fraction, it has no impact on the number or answer, because as long as the negative is somewhere, the fraction is negative. Number 3 here, -1 and 3/8 k equals 2/3. So this is a mixed number. In order to actually complete this problem and get rid of the fraction with k, which is our goal, we have to turn this into an improper fraction. The process to turn something into an improper fraction is to take the whole number aspect, multiply it times the denominator, and add that result to the numerator. So 1 times 8 is 8, and 8 plus the existing numerator, 3, is 11. So we end up with 11/8. It remains the same sign, negative k, equals 2/3. Now this problem is a lot more similar to our previous problems, where we multiply by the reciprocal, that's with the variable. And we get a -8/11. Once again, the negative being anywhere in that fraction. 8's reduce, 11's reduce, and a negative times a negative is a positive, and we get k, which is our goal. On the right side, we multiply the exact same thing. The 8 and 3 don't reduce, the 2 and 11 don't reduce, and so multiplying straight across, 2 times -8 is -16, 3 times 11 is 33. And now to close out this lesson, we have these one-step equations to end it, which these are all one-step equations, meaning you only have one step to do, whereas later we'll actually have more than one step. So this is solving by one of each method, or using each property of equality exactly once. So top left, we're adding 12 to our variable. To undo the addition of 12, we subtract by 12. And if we do it to one side, we do it to the other, and we get m equals -2. On to problem 2, we have g being subtracted by 9. And so to undo the subtraction of 9, we add by 9. And -9 plus 9 is 0, and we get g. On the left-hand side, we have to do the exact same thing by adding 9, and we get 7 equals g. Number 3, our variable is being multiplied by -7. In order to undo the multiplication, we divide by that exact same number, -7. -7 divided by -7 is 1, and we're left with 1y, or just y. On the right-hand side, negative divided by negative is a positive, and 91 divided by 7 is 13. And on number 4, a divided by 9 equals -4. To undo the division of 9, we will multiply by 9, or 9/1. The 9's reduced, and you get a. On the right-hand side, we multiply by 9, and we get -36 as our answer. And that wraps it up here for Algebra 2, Section